inducing currents in long power lines. Such a geomagnetic storm destroyed large grid transformers and shut down the whole of Quebec, Canada in March 1989, NASA reported. And this was just history repeating itself. In September of 1859, a geomagnetic storm dubbed the Carrington event caused interesting problems with the telegraph system. Telegraph operators noticed that they could disconnect their batteries and work with just the induced currents from the storm, sometimes with improved results. To this day, it is the most powerful coronal mass ejection on record. If a Carrington-level event were to happen now, it would cause widespread damage and disruption to power systems and satellites. As well as decimating electronics, any astronauts venturing beyond the protective blanket of Earth's geomagnetic field, such as to the Moon or Mars, would be in danger, something that NASA's upcoming Artemis lunar program needs to keep in mind. Considering the stakes, coupled with the fact that the sun is such a complex system, there must be another way to glean information about its future behavior besides sunspots. Other tried and trusted methods exist, but there may well be another arrow in the quiver. A U.S. and UK team led by Scott McIntosh of the High Altitude Observatory at the National Center for Atmospheric Research in Boulder, Colorado, has looked at a phenomenon related to sunspot activity. So these guys, I think, I talked about this. There was another story we did a while back that these guys were predicting that this may be a really high energy solar cycle.
Yeah.
Remember that?
Yep.
So they have a totally different way of predicting. So they're going to go through that again.
Okay.
Using data from sources such as NASA's Solar Dynamics Observatory, the team looked at extreme ultraviolet and X-ray flashes in the solar corona. These so-called bright points in the sun's atmosphere correlate with large areas of material flowing in the sun's interior, which rotates faster than surface plasma, similar to rates seen for sunspots. Robert Lehman of the University of Maryland likened it to helium balloons being dragged along by weights attached to the bottom. Such a study is potentially more useful than the sunspot cycle as it shows magnetic polarity. In the 19th century, Richard Carrington and Sporer both discovered sunspots appearing at different latitudes during different points in the solar cycle, starting at mid-latitudes and migrating towards the equator at the end. Plotted against time, this leads to a distinctive butterfly diagram. But in the early 20th century, American astronomer George Ellery Hale proved the importance of solar magnetism by showing how a complete polar flip actually spans two sunspot cycles. A flip, then a flip back. According to NASA, this 22-year Hale cycle is what McIntosh's team looks at. The bright points are markers of Hale cycle magnetic bands in the graph that I'm not able to see somehow. This begs the question of why the wider solar scientific community doesn't make for more use of such observations in this way. Folks have made use of this in the past, calling them ephemeral active regions. But predominantly they are locked into the big white whales of solar activity, sunspots, McIntosh said. Just like sunspots, the magnetic bands travel the latitudes of the sun to meet at the equator, annihilating in what McIntosh calls termination events. Remember this?
Yeah.
So yeah, they start at the higher latitudes, the sunspots do, and they're moving down, and then when they get to the equatorial region, they annihilate. But the sunspots are driven by those magnetic field bands.
Yeah.
So they're secondary effects, is basically what the McIntosh team is saying.
Yeah, that's right. Yeah.
So McIntosh's team uses these termination events to identify complete 22-year magnetic cycles, as well as the 11-year sunspot cycles of the past. Using these alongside predictions made for a 2020 Terminator event, the team predicts that solar cycle 25 will, in fact, be strong. In marked contrast to scientific consensus, they say it will be among the strongest ever recorded.
Okay, so we have a test coming up of the two methods.
That's right.
Nice.
Because the sunspot guys are like, this is going to be weak.
Or it's going to be the same as last year, or the last one.
And okay, well, let me finish the story. Right. Biesecker is supportive of the team's approach. Quote, "The work from McIntosh et al. Is very intriguing. It would be very exciting to have their prediction come true, as it would help teach us about how to better predict future solar cycles, end quote. But he does have a caveat. The Macintosh technique has yet to make a true prediction. That is, one for which there is no knowledge of the future. It's very difficult for a panel to give much weight to a technique that is new, which has never made a prediction that can be tested. He says other more traditional methods continue to be used, as they have been successful in the past and are better known. So, if Macintosh's study is right, however, what could it say about the solar interior? That the magnetic systems inside the sun are much stronger than we anticipate, and that they interact strongly to shape the production of spots, is what Macintosh says. The pressure of the magnetic field band relative to the surroundings is important. And Macintosh says, my sense is that the sun really wants to be balanced, and that we see in terms of sunspots, and what we see in terms of sunspots is the result of imbalance in that pressure, globally, locally, and longitudinally. This means they think they're only seeing the tip of the iceberg where the magnetic field is concerned. I think that's not a very good tip of the iceberg on the sun. Who is this writer? Macintosh also said that the recurrence of 55-degree latitude bands in their analysis, which
it's a Fireberg. The tip of the Fireberg.
Firebergs. Macintosh also said that the recurrence of 55-degree latitude bands in their analysis, which can be traced back through the entire observational and photographic record, is very overlooked. It suggests structural or geometric features that play a significant role in forming and aggregating the magnetic field in the sun's interior. There are still many open questions, but is the team's approach bearing out for space weather forecasting? As Lehman says, it's too early to tell, but so far the observed sunspot number and other measures such as F10.7 solar radio flux, which I guess is 10.7 centimeter wavelength radio waves, are tracking closer to our higher predictions rather than the lower panel consensus. I don't know what he means by that.
Whatever. He's saying based on those waves, their prediction is more right than the other one.
Right.
Yeah.
Whatever happens with the sunspot level, there will be some big storms, and our technological society will be impacted in some way or another during solar cycle 25. Macintosh concurred, saying, indications are that it's on track to be bigger than 24 and likely 23 as well. But we really need the termination event to happen to get real fidelity on the forecast. Macintosh is still convinced that it'll be a larger than average cycle, perhaps even in the top 10 of every one on record. But until that event happens, we won't know for sure. Biesecker is looking further ahead, saying, the relevance of the Hale cycle, as detailed in Macintosh et al., will be something for Solar Cycle 26 panel to consider. He points out that looking at the 22-year Hale cycle isn't new to forecasting, and that scientists have looked at the effects of odd and even cycles in the past, although with less skill than looking at precursors of the next immediate cycle. He says, expect the Macintosh technique to be a big part of the conversation when the panel to forecast Solar Cycle 26 convenes. Future technology could also pave the way for a better understanding of solar activity, according to, how did I say it? Guhetakurta. I spent the last 4 years at NASA Ames Research Center shaping a program called Frontier Development Lab, and got fascinated by artificial intelligence and how we might utilize our data and the tools of AI to infer patterns that can better guide physics outcomes. Machine learning and AI could be critical for understanding solar variability and climate with huge amounts of data. So that's the end of the story. I think it's really cool. This is kind of, I wish there was like, a solar Randall out there that was like just like digging through all these papers and telling us about it every week.
Yeah.
Because these guys are writing papers and they got these varying theories. And
yeah. So Suspicious Observers does that pretty well.
Oh yeah. Okay, those are the guys,
and those are daily updates. And so
That's true.
If you want like really cool sun related information, 10 minutes a day. He posts some
That's
really
right.
early.
Yeah, I have checked them out. They're pretty cool.
Yeah, they're good.
So the weird thing is the headline of this story is called "Is Our Sun Going into Hibernation?"
What?
I was like, what?
I want to know if the odd cycles or the even cycles are the ones that I want to know which ones are the ones that are in line with Earth's magnetic polarity. Because that's a big so like if so let's see if I can look it up.
you have I see what you're saying. Yeah, cuz you'll have two. Well, they're both in a way, because the two bands, the band coming from the north, its southern part is positive, right? Mm-hmm. That's the positive polarity of its southern part of the band. The northern part of the band is a negative polarity.
Yeah.
I think.
Okay.
Right? Because the band is positive.
So it's
and
not
negative.
a simple polarity like the Earth has it. It goes along.
Well, that's the way they annihilate, right?
Yeah.
And then the band in the southern hemisphere that's coming north, its northern part is positive. So the two positives hit each other and annihilate.
Okay.
No, positive and negative.
It has to be positive.
Okay,
and negative,
you're right. Dang it.
Yeah, because the positives one, if they were both positive, they
would reinforce. That's right. So yeah, they are. You're right. So then the one band on the northern hemisphere will be positive, the band on the southern hemisphere will be negative, and then they annihilate. And then the next two, the northern hemisphere band will be negative, and the bottom. So you can
look at it as an axial, like north and south.
Yeah.
Right. Yeah.
Okay.
And so I'm wondering because when the polarity of the sun of the cycle is the same as the polarity of the Earth. In other words, if the sun's north pole is also, if the sun's north side, upper part, is also the north pole, like the Earth's.
Yeah. I understand what you're saying.
Then it lines up with the Earth's magnetic field, and it's easier for these events to penetrate our field because everything's in line. Whereas when it's reversed, Earth's magnetic field acts as a better buffer against large events because they're reversed, and it's able to actually
annihilate it.
Yeah, it's actually able to because the charge comes out and it goes around. It doesn't match up, can't fit through the field. They've described it in multiple ways where it's like it's lined up with the field, and so it's able to pass through it better. More energy is able to pass through the field when they're lined up. So I'm wondering, is it odd cycles or even ones where it's lined up? I bet it's even ones. I'm just guessing, but I don't know. We don't have the watcher yet. Maybe he can find out.
Well, you should pick one.
I should just pick one?
Yeah.
I was suggesting that odd ones are where it's not lined up.
All right.
Yeah.
Cool.
I mean, that makes sense to me, but it just depends on when they started counting, really, right?
Yeah, I guess so. Or maybe they consider the polarity. Yeah, I don't know.
I mean, in my mind, I'm like, when the numbers are even, that's when it lines up because everything's even.
Okay.
And when it's odd is when it's opposed, right? I just don't know if that's how they set it up.
Yeah.
So, but yeah, it's interesting. So if we do get a stronger cycle, and it is lined up with the Earth's magnetic field, then there's potential for more damage.
I just think there's a lot. I like the way this McIntosh et al. Team is approaching the whole thing. Right.
Yeah.
I'm glad they're making predictions, and it's something that we will be able to see play out. I like their approach because their main point is it's really hard to count sunspots in solar minimum.
Yeah.
So for for at least half of the time, you don't really know what's going on. So it's hard to pinpoint, when the beginning and the end of a cycle is.
Oh, yeah, because they're tiny or whatever.
Yeah. And so that was their whole point in the last story that I read, that they were like, that when you look at the solar cycles that have been documented, this idea of an 11-year cycle is really whack. It's like way off of that. It's, on average, they can figure, well, it's roughly 11 years. But
Okay. Yeah.
because it's so hard to pinpoint based on the solar minimum sunspots.
I remember that when we were going through, Space for the News, and there's just no spots. Spots. And then suddenly a spot would appear, and he would say, and this is one that appears to be from 25 because its polarity is reversed. Right.
So it's cool that they're trying to look at it from a magnetic perspective. And,
so wait, are you telling me that like magnetism might have a big part to play in the way the sun works?
Yeah, I mean, that's what these guys are saying.
Wow. Someone should come up with a theory